The concept called center of gravity that you might have learned in IGCSE before, center of gravity is actually just a point through which the whole weight of a body is considered or assumed to act regardless of the orientation of a body. Now, why do we have center of gravity in the first place? It's because it is for ease of calculation. If I were to give you an object that looks like this, and I tell you that the weight of the object is 10 Newton for this entire object, what actually is happening for that object is that the weight is actually spread throughout the object. It could be that there's, say, 2 Newton here, 2 Newton here, 2 Newton here, 2 Newton, and also 2 Newton here. Added together will give you 10 Newton. But when you want to do calculations for this object with all the weight spread out like this, is a bit complicated. So what people have done is that, why don't you just assume that the whole weight is acting at a single point called the center of gravity. This will make your calculation a lot easier. So that's why we have the concept of center of gravity, the point where you assume or consider the whole weight to be acting. Okay, it isn't to say that all the weight is acting there in practice. It's just that you assume it is acting there. So this part here where you say considered or assumed to act is very important when you want to do the definitions. Okay, now center of gravity tends to act at the center of geometry. All right, so if let's just say we give you a few uniformly shaped objects like this, the center of geometry is usually the center of that object there. That is where your center of gravity is. Okay. Now, if you have a non-uniform object, the center of gravity will usually be towards the heavier side. But this one, I don't think you need to worry. In your exams, we normally don't even bother about this. You just need to know that center of gravity will usually act at the center of geometry of the object, meaning to say at the center of the object. Okay. Now, then we go to something that will be new to you, moment of a force. Okay. Now, you know that before this, force can cause an object to move, it can cause an object to speed up, it can cause an object to slow down, and so on and so forth. You will also know that force can also deform an object. Force can also do something in the sense that it can make an object rotate. You see, if I have something like this, a bar that's attached to maybe a pivot here or a pin, if I were to apply a force at this end here, what will happen is that because this pivot or pin is fixed in place, if I were to apply a force here, it will cause the bar to rotate. Okay, force can cause rotation, and the ability of a force to cause rotation is measured by what we call moment. Okay, so the higher the moment of an object, the larger its ability to turn an object. Okay, it is described as moment, measured in units of Newton meter. All right. Now, if we are asked to define what is a moment in your exam questions, you will just say the moment is the product of force and perpendicular distance of the pivot from the line of action of the force. So over here in the diagram below, the diagram here is actually the same thing that you see here. If I tell you that this is the pivot and then this is the force that you apply, to find out what is the moment caused by that object, you would take the force multiply with its perpendicular distance. Okay, product of force and perpendicular distance of that force from the pivot. Okay, so this is what we will do to find out the moment of an object. Now, moment may sometimes be known as torque, right? Sometimes when you read your questions, they may say moment in one question, and then another question they may say torque. They're actually the same thing. Okay, they are interchangeable. All right. Now, moment or torque is a vector quantity with directions either clockwise or anti-clockwise. If you refer back to the diagram where you have a beam attached to a bar, Your rotation can be two directions depending on how you apply your force. You could have either a rotation clockwise, in this case we say clockwise moment, or you could have a rotation anti-clockwise. In this case, we say anti-clockwise moment. All right, this is one thing you need to know first. Moment, just like force, is a vector. But in your case now, the direction is usually only two types, clockwise or anti-clockwise rotation. Okay, there will also be cases where you try to find moment of a force, but the diagram isn't as straightforward. It could be that the force is not perpendicular to the pivot. The line of action of the force is not perpendicular to the pivot, like what you see here. What you see here is the same beam or same bar, but the force is no longer acting straight like this. Instead, it acts at an angle. So when you want to find the moment caused by this force right now, there are actually two ways in which you can do this. The first way is that you extend the line of action of the force so that it approaches the pivot. If I know that this is the pivot is the point through which your object will tend to rotate. I think I already wrote it in the page before this. I wrote it, pivot is the point through which your object will rotate about. Okay, so if you want to find out what is your perpendicular distance indicated by this blue line here, what you can do is that you can try to extend the line of action of the force going towards the pivot itself. If this is your pivot, you can extend your force either forwards or backwards. You can extend it backwards or you can extend it forward. So how do you know where you want to extend it? You try to extend it towards the pivot so that it approaches the pivot. When you extend it so that it approaches the pivot, you can clearly see your perpendicular distance already. Okay, so extend the line of action of the force, then you will see that the perpendicular distance is indicated by this dotted line here. Now, if you have trouble visualizing what is perpendicular distance, the easiest way I can tell you is this. You try to visualize it as the distance between the line of action of the force and an imaginary line drawn parallel to the force that passes through the pivot. What do I mean by that is this. If you have a force that looks like this, and your pivot is here, you want to find out exactly what is the perpendicular distance, you draw another line that is parallel to the force but passes through the pivot. So what you will do is that you will draw something like this. What you will do is that you do something like this. You draw an imaginary line that is parallel to this one, parallel, and passes through the pivot. Then you'll be able to see very clearly what is the perpendicular distance. Okay, so if let's just say you're lost on how to determine what's the perpendicular distance, just draw an imaginary line through the pivot and make sure it's parallel to the force that you're looking at. You'll be able to see very clearly what's the perpendicular distance, right? So once you extended the line of action of the force and identified out your perpendicular distance, your moment, let me just change the color. Your moment is still force times perpendicular distance. You're just going to take F times X. All right. But X here, the perpendicular distance can be expressed in terms of angle theta and D. If you recall your trigonometry, if this is X, this is D, and then this is theta, sine theta is X over D. So X is D sine theta. That's why you get this. Okay? So F is multiplied with d sine theta. Your resulting expression is F d sine theta. This is the moment of force for this diagram here, obtained by you extending the line of action of the force. There is also another different way. This one is actually more common. This is by you resolving your forces. So you again have the same diagram as before, but rather than extending the line of action of the force, you resolve the forces. So this was the original force that you have at angle theta. So what you do is that you resolve it into two directions, this one and this one. Now this one is adjacent to the angle, so it's f cos theta. This one, if I were to shift it here so that it completes the triangle, is opposite to the angle. So it's going to be f sine theta. Okay. So what you then do is that you again use the same formula. Moment is equals to force times perpendicular distance of pivot. But this time you look at it, that although there are two forces, you really only need to consider one force only for the moment calculation. If I ask you to look at the f cos theta, notice that if I were to extend the line of action of the force, it actually passes through the pivot. So f cos theta passes through pivot. There is f cos theta passes through pivot. There is no perpendicular distance, therefore no moment. Okay, so when you want to find out the moment caused by the forces right now, you may have thought that you needed to consider f cos theta and f sin theta, but the fact is that you actually don't need to consider this, because you see the force passes through the pivot. When it passes through the pivot, there is no perpendicular distance, so there's no moment, because moment by right is force times perpendicular distance. If this one is 0, this one will be 0. Okay, so in general, what we'll tell you is that any force that passes through the pivot will not have moment produced because there's no perpendicular distance. Okay, so f cos theta you don't consider. You only consider f sine theta. So now your perpendicular distance of f sine theta to the pivot is actually just going to be d. You see, if I were to draw a line parallel to f sine theta passing through the pivot, you will see very clearly that this one is actually my perpendicular distance given by d here. So to find the moment caused by this force, I take this force multiplied by this perpendicular distance. That's why I get f sine theta times d, which in turn gives me f d sine theta. You see, this expression that you have here is actually the same as what you have above. If you extended the line of action of the force, you got the moment as f d sine theta. If you were to resolve the forces, you're also getting the moment as f d sine theta. Both will still give you the same answer. Okay, but usually in your exam, it is more common to use resolving the forces to find the moment. Extending the line of action of the force is acceptable, but some cases it cannot be used. It's difficult to use. It's better to resolve the forces. Okay, so if you look at page 5, which is the next page on the examples, you have a uniform beam of weight 60 Newton and length 0.8 meter that is pivoted at point A. Determine the moment of the weight about point A. Okay, now there are some things here that you need to realize. They say that this is a uniform beam. Okay, now whenever you hear mention of something called uniform beam, this means that the weight is acting midpoint of the beam. Okay, it's a uniform beam, meaning to say the cross-sectional area is uniform. If I give you some example of a beam, this one here is considered to be non-uniform because you can see that the cross-sectional area is varying as I go along the length. this one here, if I draw it nicely using a ruler, this one is considered to be uniform, right? If I tell you it's a uniform beam, your weight would act exactly at the center, given that if say this one is L, your weight would act exactly at the middle, at L over 2, okay? But if it's a non-uniform beam, usually the weight will not be exactly at the center. Say if this one is length L, okay, same thing, length L. If this is non-uniform, your weight will not be acting right at the center like the uniform beam. It will be towards the heavier side, okay, towards the heavier or larger section, okay. This is for non-uniform beam. But most of your case in your exams is all uniform beam. They will specifically tell you it's a uniform beam. So the moment you see the mention of uniform, straight away the association that you should have in your mind is that weight is right in the center. So the uniform beam of weight 60 Newton, length 0.8, pivoted at A. A is your pivot. So where is your weight acting now? If this one is W, and your length is 0.4, it should be acting at a distance of 0.4 meter and 0.4 meter here. Okay, this is what you can see now. So they want you to determine the moment of the weight about point A. So moment of the weight about point A, what is the moment caused by this weight about this point? So you already know that moment is force times perpendicular distance. Your perpendicular distance will be indicated by this. Sorry, let me just erase the color. Can I use purple maybe? This is your perpendicular distance. Again, you see if you draw a line parallel to the force passing through the pivot, you see easily that this is the perpendicular distance. This one will be 0.4 minus 0.15. Okay, so this one is 0.4 minus 0.15. You want that distance there, it will be 0.25. So your moment now is weight of 60 Newton multiplied by 0.25, giving you 15 Newton meter. Okay, unit of moment is going to be Newton meter, because you see moment is force times distance, right? Force has unit of Newton, distance has unit of meter, so multiplying both together you're gonna get Newton meter, right? So that one is okay. Now then after that, the question mentioned to you in part B, another force of 100 Newton is acting at 30 degrees to the beam as shown in the diagram. Determine the resultant moment of the forces about point A. Okay, so I'm just going to clean out some of the things here. I'll erase the non-relevant parts. The 100 Newton force is the force that you see here at 30 degrees. All right. So let me just erase off everything here. And let me just erase this. Sorry. The weight is still here. Okay. And then the distance that you have here is 0.25 meter. You already established that. Okay, now you have a force of 100 Newton acting at an angle of 30 degrees to the beam. There's something wrong with the diagram here. The 100 Newton went away and then the angle actually went off the diagram. Okay, so the 100 Newton is this one acting at an angle 30 degrees. When you want to find the resultant moment, they're actually asking you to find out what is the total moment caused by this weight and this force. So again, you see this force here is at an angle. It isn't really strictly horizontal or vertical, so it will be difficult for you to find the perpendicular distance. What you would do is that rather than extending the line of action of the force, if you extend the line of action of the force, you will extend it like this, and then you find your perpendicular distance here. Okay, this one is according to the first method that you learned before. But rather than doing that, why not we just resolve the forces? If I resolve the forces, I am going to get this force and this force. So the horizontal force will be 100 cos 30 because it's adjacent to the angle. The other one must therefore be 100 sine 30 because by now you should know it will be adjacent, it will be opposite to the angle. All right. Okay, so now you have actually a few forces to consider. The moment caused by a few force, the turning effect caused by a few force. You have the weight, you have the 100 sine 30, and then you have the 100 cos 30. Okay, but one thing here you can see, you can simplify already, is that 100 cos 30 actually passes through the pivot. So this one don't consider because it passes through the pivot. You will really only need to consider this and this. Okay, so how will you find the resultant moment now? I'll just write the workings at the top right hand corner here. Now, when you want to find the moments, moment, as I mentioned to you, is a vector. There is an associated direction to it, either clockwise or anti-clockwise. So if it's a vector, there's a direction to consider. That also means that you will end up having positive or negatives for vectors. So right now, you see the weight W here, if you try to imagine how this weight W will cause this beam to rotate about the pivot, you will see that it will tend to cause a clockwise rotation. Maybe I use a black color highlight. Yeah, you will see that it tends to cause a black color. You tend to cause a clockwise rotation. Weight W, if you try to visualize the rotation of this beam about the pivot here, it will tend to cause a clockwise rotation. But the 100 cos 30, if you try to visualize the rotation of the beam about this pivot here is fixed, okay, it cannot move, only the beam can move, you will see that the rotation caused by 100 sine 30 is counterclockwise. If this is clockwise, this is counterclockwise. Okay, so you clearly have two different directions here for the rotation. One of them has to be negative. So similar to the previous chapters you've done before this, when you want to add forces to find resultant force, you need to establish something like a sign convention. So say for example, right now, if I consider clockwise, maybe, yeah, if let's just say I consider clockwise rotation as positive, my moment now would be equal to W, if I consider this one, the moment caused by the weight would have positive moment. The moment caused by 100 sine 30 will be negative moment. Maybe I just write it here. Again in black. This one is positive moment. This one is negative moment, according to my sign convention. All right. So you put in all your moment caused by the forces. If I consider the weight, it will be 60 times 0.25. We already did this just now. How about the 100 cos 30? The 100 cos 30 will be negative moment because you see it's counterclockwise. What is the perpendicular distance for this force to the pivot? Same thing as before. You can see that it's going to be this one. So this one will actually be 0.4 plus 0.25, giving you 0.65 meter. So this one will be 100 sine 30 times with 0.65. Okay, so remember that there's a negative here. So you try to simplify this. 60 times 0.25 minus with 100 sine 30 times with 0.65, you're going to get negative 17.5 Newton meter. Okay, so what is the significance of this negative here is that it's saying that the resultant is acting counter clockwise, opposite to sign convention direction. Okay, because the sign convention was clockwise positive, if you get a negative, it just means that it's supposed to be acting the opposite direction. Okay, so this is one example on finding moments. So far, so good.
Yes, sir.
All right. Okay, so if this is okay, then you look at part 2. I'm just going to clear out the drawing. Okay, now this one somehow looks easier in the sense that they don't have any diagonal forces. This one is actually just testing you on how you find out your perpendicular distance. Okay, so the question here is asking you, find out the resultant moment at point P. Okay, P here is your pivot. They want you to find out the moment caused by all these forces. There are in total 4 different forces. What's the resultant moment about point P? So let's just go through this one by one. Okay, let's just say right now the previous example I use, I just use clockwise as again as positive, right? Let's just say right now moment clockwise is positive for me. What is the resultant moment here? Okay, we go through the forces one by one. The 15 Newton force, if this is my pivot, the 15 Newton pivot again is the point about which my object will move, will rotate about. Okay, it's not supposed, the pivot itself cannot move, right? But anything else attached to the pivot is supposed to move. So the 15 Newton force that is acting here right now, if you try to visualize what will happen, if you assume that this entire beam, this one is an entire beam, okay, it's a L-shaped beam. Okay, it's an L-shaped beam. It's a solid structure, L-shaped. All right. So if you have a 15 Newton force right now acting here, the direction of rotation caused about the pivot, caused about P, would be like this. It's clockwise, so this one is positive moment for you. But what is the perpendicular distance? So draw a parallel line passing through the pivot. You can easily see that this is now your perpendicular distance. Okay, because if you draw it like this, you will see that this one is the perpendicular distance. So this one will be 50 times with 0.3. Now we move on to the 100 Newton force. The 100 Newton force, if you try to visualize what is the direction of rotation caused about P, again, it will be clockwise. So it's going to be positive moment. But what is the perpendicular distance? You draw a parallel line passing through pivot like this. This one is by right your perpendicular distance. So it's going to be 0.1. Okay, it's going to be 0.1. So this one again will be positive 100 times with 0.1. Now we go to the 200 Newton force. If you're trying to visualize what will happen to this 100 to the beam when a 200 Newton force acts here, it will tend to cause a rotation like this. This is counterclockwise, opposite to your sign convention. So it's negative. But now what is your perpendicular distance? Again, draw a line parallel to your parallel line passing through the pivot. This one by right should be your perpendicular distance. Okay, so this one actually should be, how much should it be? Okay, this one here, this is 1.2. Yeah, this one, you want this distance, right? Okay, right, let me just erase this. You see that this is 1.2 for the whole length, and then this is 0.7. So you take this minus this. So this distance here is 1.2 minus 0.7, giving you 0.5 meter. So this is negative 200 times with 0.5. Okay, then we move on to the last force, which is 50 Newton. The rotation caused by this force about point P is going to be counterclockwise, opposite to your sign convention, so it's negative. Again, where is your perpendicular distance? Draw a parallel line passing through pivot. This is your perpendicular distance. Okay, yeah, maybe I shouldn't have overlap. This one is your perpendicular distance. Okay, to get this distance, what you do is, you know this is 0.3. You know this is 0.1. It's actually just a simple matter of adding them together. So this one will be 0.3 plus with 0.1, giving you 0.4 meter. So this one will be negative 50 times 0.4. So 50 times 0.3 plus 100 times 0.1 minus 200 times 0.5 minus 50 times 0.4. You get negative 95 Newton meter. Okay, so same thing as before, because you're getting a negative value here, it just means that it's supposed to be acting counterclockwise, opposite to your direction of sign convention. You could have repeated this calculation again, but this time where you assume your sign convention is counterclockwise positive, your answer will still be the same in terms of magnitude, but you won't get negative anymore. You will get positive. Okay, if you repeat the calculation where your sign convention is counterclockwise positive, then you will get positive. But magnitude-wise, it will be the same. Both will still tell you the same story. Correct magnitude, correct direction. Okay, so this is called finding moments. So far, so go with this.
Yes, sir.
Okay, so this one is okay. Okay, then we take it one step further. We talk about torque of a couple. Okay, just like I told you, torque and moment are basically the same thing. Okay, now specifically we talk about moment or torque of a couple. All right, now when we talk about couple, a couple is just a pair of equal but oppositely directed parallel forces whose line of actions do not coincide. A couple must be equal magnitude but acting in opposite directions, and they must be separated by a distance. Okay, so if you look at the example of the steering wheel here, you notice that there are a pair of forces, 15 Newton, equal magnitude, but acting opposite directions. And also you notice that they are not in line with each other. They are separated by a certain distance, 0.4. This is what we call a couple. If you had 15 Newton and also 15 Newton like this, yeah, sure, this is equal opposite force, but they're not separated by a distance. So this one is not considered a couple. Couple must be equal opposite force, but separated by distance. Okay, this one I'll just write here. Not couple because no separation. Okay, this one is couple, correct. This one is not. Okay, now a couple will tend to produce only turning effect and won't produce any linear motion. Now, if you just consider the forces linear, you just consider the forces linearly in the linear direction, you have 15 Newton acting outwards. You have 15 Newton acting outwards, you have 15 Newton acting downwards. This one, you have no resultant force vertically. Okay, you have no resultant force vertically, therefore no motion. Okay, to move you need to have a force in the first place, but since you have no resultant force, you're not going to have any motion. Okay, no resultant force vertically, no vertical motion. Okay, i.e. no linear motion. Okay, but then again, you see that same force, if you try to see whether do they cause any rotation. If I tell you that the center of the steering wheel here is the pivot, this 15 Newton force will cause a rotation clockwise. This other 15 Newton force will also cause a rotation clockwise. You see, this moment is the same direction as this moment. Both are clockwise. They're not cancelling each other out like the linear 15 Newton force. Okay, if you're talking about the rotation cause, instead of looking at the forces, the rotation is actually the same for both. They're both in the same direction. Okay, so if I wanted to find out what is the resultant moment or torque caused by this pair of forces, I could make use of what I learned earlier, what I used earlier, where I tell you that moment is force times perpendicular distance. This one here I told you is the distance between the force and pivot. This was the one that you learned before this. If this is your pivot, this one was 0.2 meter. This one will also be 0.2 meter. Okay, so this one will be 15 times 0.2 plus with 15 times 0.2, giving you 6 Newton meter. But then you notice one thing, if you try to simplify this further, it's the same as 15 times 0.2 plus with 0.2, which in turn is 15 times 0.4. So you notice that this 0.4 is actually this entire distance here. Okay, it's actually the distance between the forces. Let me just write another thing. It's actually the perpendicular distance. It's more accurate to say that. It's the perpendicular distance between the forces. So torque of a couple can be expressed as this instead. 15 times 0.4 equals to 6 Newton meter. Okay, so when you are asked to find out the torque of a couple, you can actually just say it's the product of one of the forces and the perpendicular distance between the forces. Okay. If it is, yeah, that's why now you see that there's some duplication in the equation. This one is force times perpendicular distance. The one that you learned before this, moment is equal to force times perpendicular distance. This one is for non-couple forces. The one that you see here, moment or torque equals to force times perpendicular distance. This perpendicular distance is actually between the forces, not the pivot. Okay, this one is for couple forces. Okay, so there's some similarity in what you see in terms of the equation, but the distance that you use is slightly different. It depends on what is the nature of the force. If it's not a couple, you don't see equal opposite force separated by distance, you want to find the moment or torque, yes, you will use this, but that distance will be between the force and the pivot. But if it is a couple force, again, it is force times perpendicular distance, but that distance will be between the forces themselves, not the pivot. Okay? So torque of a couple is just product of force and perpendicular distance between the forces. Right? So that one is something that you just need to know for now. Okay, then you look at the diagram below here. Let me just clear all the diagram. Now, which of these examples here are a couple? A is not a couple. Why? Because what's wrong with this diagram? It's because this one is not opposite direction. How about B? B is also not a couple because not equal magnitude. Yeah, it's opposite direction and there's distance separating them, but there's not equal magnitude. For A, you have equal magnitude separated by distance but not opposite direction. Okay. Now how about for C? See, this one is couple. Equal magnitude, opposite direction, and there's a distance separating them, which is this one. This one is good. How about for D? D is something that I actually just now mentioned already. It's not going to be a couple. This one is not a couple. What's wrong with this is that there is no distance. I think I better use a proper term here. No perpendicular distance between the forces. Okay, so only C will be considered as your couple. So this one is okay. Now, if you look at the other example, the length of the beam is 25 centimeters. Determine the torque of the couple shown. Okay, if this one you already identify is the torque, sorry, is a couple because you see equal opposite force separated by distance. They want you to determine the torque. This one is very straightforward already. Is torque equals to force times perpendicular distance. But your perpendicular distance now, bear in mind, is supposed to be this. This is your, sorry, you can't see the blue correctly here. Your perpendicular distance is this one here. Okay. Now the 25 centimeter that you see here is actually for this diagonal length. You don't have the perpendicular distance. You have to find the perpendicular distance here. But this one, you know, you from your first chapter, you can actually resolve this 25 centimeter into the vertical component, isn't it? This one is actually going to be 25 sine 30. So now your torque is equal to 100 times 25 sine 30. Wait on sine 30 times 25 times 100. You're going to get 1,200. Oh, sorry. There's one mistake that I made here. I did not change it to meter. Okay, I need to change it to meter. This one is in centimeter. I need to change it to meter. Sorry. Let me just write it out here. This is in centimeter. I need to change it to meter. Will be 0.25 sine 30. So 0.25 sine 30 times with 100, you're gonna get 12.5 Newton meter. Okay. This one, your rotation, you can easily see is just gonna be clockwise. Okay, there's no need to have a sign convention here. Right, so this is for this. Then after that, we just go through a few more things for moment over force and torque. Okay, if you look at the next page, moment over force depends on the pivot about which the moment acts. The further the force is from the pivot, the greater the moment. It is affected by the perpendicular distance of the force from the pivot. Okay, why do I need to highlight this? Is because later you see a different case for moment of a couple or torque of a couple. Just now I already mentioned to you that moment for non-couple is force times perpendicular distance, where this one is between force and pivot. So now, if I give you a few cases here right now in this diagram, I ask you to find the moment of the 100 Newton force about three different pivots, A, B, and C. You will probably say that the moments is all going to be different just by looking at this, which is true. But let's just find out first what are the values. This one you see, wait, let me just scroll down later so that it's easier to see later. Okay, so now I want to find moment about point A. It will be 100 times with 0.6 because this one here is 0.6 meter. So this one I get 60 Newton meter. Okay. How about moments about point B? Right, this one was taking moments about point A. The force 100 Newton, the perpendicular distance is 0.6. I get 60 Newton meter force. How about if my pivot is now point B? My perpendicular distance is now going to be 0.4 meter. So this one would be, again, 100 times 0.4 equals to 40 Newton meter. Now I'll go through the last point, pivot C. The perpendicular distance is just going to be 0.2 meter. So it will be 100 times 0.2, giving me 20 Newton meter. Okay, so now you can clearly see that the values are different because the distance of the force from the pivot is varying. Okay, so that one is okay. But now let's change the question a little. Rather than having a non-couple force, rather than having a single force here, why not we have the same beam, but we have a couple? Okay, so here I mentioned that a couple is different. The torque of a couple will only depend on the perpendicular distance between the forces. It won't depend on the distance from the pivot or the location of the pivot. So just now I mentioned to you specifically that for couple, M is equals to force times perpendicular distance, where the perpendicular distance is distance between forces, not pivot. Okay, so now if I look at this one right now, my torque is just going to be 100 times 0.2. If I use the same formula, my couple right now is this one. The perpendicular distance between them is 0.2. If I just do this one is 100 times 0.2. I'm getting 20 Newton meter. Okay, so just bear this in mind first. If this is calculated using this equation, now if I try to calculate the torque of this couple, not by using this equation, but using this equation instead, you will see that the values are actually the same. What I mean by that is, again, now let's just say I take moments about A. This is my pivot. Let's just say that going anti-clockwise is positive now. Okay, let's just say right now for the sake of our discussion, going anti-clockwise is positive. So for pivot A, this one will go this way. This is negative. This will go this way. This is positive. So this one will be negative 100 times with 0.4 plus with 100 times 0.6. So you're going to get 20 Newton meter. Okay, this is if I take moments about A using this equation put here. Okay, if I use this equation, all right. Now if I go on to moments about B, same sign convention, anti-clockwise is positive. Basically, I'm just using the same now. I don't need to write the whole thing again. I'm still using anti-clockwise as positive. MB, this is now my new pivot. I draw the line here. This is now my new pivot. 100 Newton will still be negative. 100 Newton will still be positive here. Okay, so this one will be negative 100 times with 0.2 plus with 100 times with 0.4. Again, you will get 20 Newton meter. So let's repeat this for the last one, last pivot. Pivot C. Okay, I use green color. Let's repeat this for the last one, pivot C. Okay. Now for pivot C, this one is a bit more straightforward. If you look at pivot C alone, the 100 Newton force is actually passing through the pivot. So this one, no moment to consider. All right, you will only need to consider this 100 Newton, which by now you see is causing anti-clockwise rotation, so it's positive in the first place. So this one will be equal to 100 times with 0.2, again giving you 20 Newton meter. Okay, so now you look at this one, MA, MB, MC, where you calculate out the resultant moment or resultant torque by summing out the forces, by summing them out individually. You see the values are all the same. 20 Newton meter, 20 Newton meter, 20 Newton meter. Although the pivot location varies, A is here, B is here, C is here, I'm still getting the same value for all of them. Okay, that's why here I mention if you're talking about couple, it won't depend on the distance from the pivot or the location of the pivot. It really only depends on the perpendicular distance between the two forces. You see, when I try to find the resultant moment or torque by using this equation only, where I only use the perpendicular distance between the forces, this is what I got. If I didn't use this and I use this instead, where the location of the pivot varies at the same time, you notice that the values are also still the same. That's why it won't matter if it's a couple. If it's a couple, pivot location doesn't matter. It doesn't do anything. Okay? Right? So far, so good.
Okay, sir.
Okay. Right. So, is there anything else I can write here? Let me just erase all certain things. Okay. Yeah, maybe this one I'll just write in here somewhere. Location. I'll just write in black here. For this tree, location or pivot does not affect torque of the couple, torque or moment of the couple. All right. So based on these three values that you see here, location or pivot does not affect moment or torque of the couple. So might as well just use this one straight. Right? As long as you see couple, straight away use this. Don't bother using the ones that you see earlier here. And this one is specifically only for non-couple forces. All right.
Okay.